Hi, my name is Guilherme Brando, and I'm a third-year PhD student at the Universidade Federal do Espírito Santo in Brazil. Today I'm going to talk about relativistic corrections to the growth of structure. This talk is based on the work I've done in collaboration with Professor Kazuya Koyama and Professor David Watts, both of them at the Institute of Cosmology and Gravitation at Portsmouth. Our idea was to implement a way that we can make Newtonian simulations relativistic in a fast and computationally low-cost manner. For that, we used the n-body gauge formalism, in which the spatial trace part of the metric is set to 0, and the temporal slicing of the metric is set to the comoving gauge, in which the shift perturbations are the same as the for velocity. By doing so, the relativistic equations of motion assume a very similar way to its Newtonian counterpart, in which the main difference, the only difference, is the source term on the right-hand side. This source term on the right-hand side is where the relativistic effects are encoded. And the source term is given by the sum of all the density perturbations of the relativistic species, photons, neutrinos, and dark energy, plus an additional term that comes from the metric. This additional term that comes from the metric is written and depends on the first and second derivative of the traceless term of the spatial metric and in the anisotropic stress of all the matter species. Since in the n-body gauge we can compute the traceless term of the spatial metric solely in terms of these fluid quantities over here, the anisotropic stress, the pressure perturbations, and the total velocity divergence, we can implement this n-body gauge formalism inside any Einstein-Boltzmann solver and compute the source term and make relativistic simulations. We summarize our results in this plot over here, where we can see that the small-scale physics is completely the same as in the Newtonian case, so there is no relativistic effect coming from here. And all of the relativistic effects are only present at large scales, where we know that linear theory, in which our formalism is based on, linear theory holds. So these is our main results, and you can find it more on our work over here. In summary, we have implemented in high class and class, and it's going to be soon available to the community, a fast and computationally low-cost way to make any Newtonian simulation relativistic without any need of post-processing. Thank you very much.